Right, so this unit is about infinite series. We're going to be interested in the topic of convergence. Does the series converge or does it diverge? And so that's kind of what we're going to be digging into over the next several weeks is what exactly does that mean and how do we decide those sorts of things. So in Algebra 2 and in Algebra 1, you dealt with sequences. So a sequence is just an ordered list of terms like 1, comma 2, comma 3, comma 4, comma 5, dot, dot, dot. You can either have a list that has finitely many terms and ends, or it can be an infinite sequence with the dot, dot, dot that goes on forever. If you change all those commas to pluses, 1 plus 2 plus 3 plus 4 plus 5, dot, 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 or that you stop, then that is now called a series. And so the value of the series is the sum of all of those terms in a sequence. So the question is, if you add up an infinite number of things, is it possible that there is a finite result? And the answer is yes. We've seen that with like the improper integrals that we looked at. You can find the area under a curve from 1 to infinity and have it approach a finite value. And so that's kind of a similar strategy we're going to look at here. Here's an example of kind of a common infinite series. So we take a half plus a fourth plus an eighth plus a 16th. The next one would be plus a 32nd plus a 64th and so on. So if we are to add those fractions up indefinitely, will we have a finite sum or will it be infinite, meaning it would diverge? So this is a good one to look at geometrically. If we think about this as a square with an area of 1, then what we have here is half of that would be a half, and then the following square, half of what's left makes a fourth, half of what's left, makes an eighth, half of what's left makes a 16th, and so on and so on. If you're constantly taking half of what's left, no matter how teeny tiny this is going to get, do we really have are we ever going to fill the square? And the answer is no. We're going to get closer and closer and closer to filling the square, but we're going to have these infinitesimally small little bits of area left over. And so even if we continue this pattern on infinitely, the sum of all the terms in that series is going to be a total of 1. So that's kind of interesting. Now, it is really hard to tell just by looking at the series what is going to happen. Here's a couple of examples. 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4. The question is that going to diverge or is it going to converge to a specific sum? Now, you may look at this and think, well, the fractions are getting smaller and smaller and smaller. But what if they're not getting smaller fast enough? And so we can't really tell just by looking at it. That's an example that represents the harmonic series. The one below it is an example of an alternating series. 1 minus 1 plus 1 minus 1 plus 1 minus 1 plus 1 seems like it might just be 0, but it depends on if you're looking at an odd number of terms or an even number of terms. So there's going to be different rules for alternating series like that. We can't really tell just by looking at it, so we're not quite clear. Here's two things that are very important to consider as we move forward throughout this unit. 1, we have to make sure that we understand that the rules for a finite number of terms do not apply to those for an infinite number of terms in a series. So that would be things like the commutative property or the associative property. So for example, on this 1 minus 1 plus 1, I could choose to group it as 1 minus 1 in parentheses plus 1 minus 1 in parentheses plus 1 minus 1 in parentheses, and then it would look like I'm doing 0 plus 0 plus 0 plus 0 plus 0. Or I could choose to group all the positive ones together and all the negative ones together, which may or may not yield the same result. So the general rules of real numbers really only apply if there's a countable number of terms in your series. If there's not, those rules can't be treated the exact same way. Secondly, is that a finite sum always produces a real number, meaning it converges, because if you know exactly what things you have, you can find their sum. But an infinite sum might or might not, and that's really what our focus is for this whole unit. So the first strategy that we're going to look at today is partial sums. So an infinite series is going to look like this: a1 plus a2 plus a3 plus dot 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 out to a sub n plus dot, 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 out to infinity. Now, if we go to infinity, the notation we use is this capital letter sigma that represents summation. We've seen that before. And so this particular one is starting from the I minus 1 term and going out to infinity. So the first one, like if I want the first term, that would be if A1, that's going to be 1 minus 1, so that's from 0, like your initial position kind of thing. But this summation means use this pattern starting at the number here on the bottom. The pattern here would be A sub I, and add up those terms individually over time. So partial sums is looking at a finite set of terms. So for example, if I want the first partial sum of a series, then I just want the first term added to nothing because I'm only looking at one term. The second partial sum would be the sum of the first term plus the second term. The third partial sum would be the first, second, and third terms added up, and so on. The nth partial sum is going to be the sum of the first n number of terms. So we're not going to infinity here on the top. We're only going to whatever number we're choosing for n. So the first strategy that we're going to look at to determine convergence is to look at the limit of the partial sums. So if I look at a series of partial sums as n approaches infinity, if that value seems to be converging to some number L, then the series is going to converge to that number L. So let's look at an example. If I have the series 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7 minus 8 and so on and so on and so on, I can look at the first few sums. So the first sum would just be the first term 1. The second partial sum would be 1 minus 2, which is negative 1. The third partial sum, 1 minus 2 plus 3, which is 2. And if we keep on going, we see that we go from 1 to negative 1, 2 to negative 2, 3 to probably negative 3, 4 to probably negative 4. So the partial sums are approaching either positive infinity or negative infinity. It's like their values are oscillating. So here we can make the assumption that the series diverges. Okay, here's a different example. Example 2, we have 25 over 100 plus 25 over 100,000, nope, 10,000 plus 25 over a million, and so on. You can tell the pattern is that we're doing 10 to an even power. This is 10 squared, 10 to the 4th, 10 to the 6th, and so on. So that's kind of what our general term looks like. So if you evaluate, that first term is 0.25, the second term plus the first term comes out to 0.2525. The third, if we add up these three things that we have here, we get 0.252525. The fourth term would be the next one. We would have 8 zeros down on the bottom, and you can see what's happening. These values are approaching 0.25, repeating. It's getting longer and longer the further we go out, so we can assume that this series converges to 0.25, repeating because that's the limit of our partial sums. Okay? There's a couple more examples. Well, there's one more on here. This is the example that we looked at the beginning. 1/2 plus 1/4 plus 1/8. We saw geometrically that that converges, but here's an example using the partial sums. We have a half, then a half plus a fourth is 3/4. A half plus a fourth plus an eighth is 7/8, and so on. And you can see these values are getting closer and closer to a sum of 1. So that is all that you need to be able to look at on this first day, is looking at partial sums. Our studies in this unit are going to be looking at several different convergence tests, which help us decide whether they converge or diverge. So something to look forward to. I will see you guys later.